Hey everybody, we're going to finish up our last note in organic chemistry today. Hopefully this is my third try to make this note, and the last two times it's crashed near the end, so I'm hoping to get through it. I may cut it halfway and then come back and finish it in a second part. Anyway, so I hope you're well. I did send you out updated marks yesterday, and I'm hoping that inspires you to get done some of the things that might be missing for those of you who aren't up to date. Again, all those things that are zeros, just bring your mark down. So if you can get rid of the zeros, every zero that goes brings your mark up. So, yeah, try not to let those things bring your mark down if possible. Okay, so I want to start with taking up the 3 questions from last night's homework. This is such an important part of organic chemistry. I really want to make sure that we're all on top of this as we move forward into this last section because, like I said before, organic is such an important part of chemistry. Now, I want to look at the questions here on page 142. Right, so I'm going to switch back to my textbook. Before I do that, I just want to quickly go back to this chart because it's such an important chart for us. Looking at basically 4 important molecules or 4 families today. One are the haloalkanes. Right, that's when I've got a hydrocarbon with a halogen. Remember, the halogens would be either Br, Cl, I, or F. Those are your 4 halogens, and they'll be the X that I see there on that molecule. The second family are the ones that have an OH group, a hydroxyl group on the hydrocarbon chain. That's a massive family of organic compounds called alcohols. We're going to talk today specifically about a group called the carboxylic acids. We talked about these in chapter 3. The terminal carbon, the end carbon on my chain, has got a double bond to O and a bond to O, which also has an H on it. So that's a carboxylic acid. And then my last group that we're going to talk about today are the esters. And the esters have got C double bonded O and another O. And instead of the O having a hydrogen on it like I have up here, I'm going to replace it with a C and more of a hydrocarbon on the end here, and that molecule is called an ester. So I can see here, there's my C double bond O. The O at the end here is bonded to another hydrocarbon structure, while the C double bond O, the ester, is linked to more hydrocarbon. All right, so you can see how that C double bond O links together 2 hydrocarbon groups. Now, I want to move on today to look at the beginning of chapter 4, actually taking up the homework from yesterday first. Okay, so to take up the homework, question 9 says, predict the type of compound that would form in each of these reactions. Do not need to name or draw. It just says, what would you expect to happen? Well, again, I'm going to actually draw them. That way we get a sense for what's going to happen. So an alkyne, remember, has a C triple bond C, right? And what's going to happen if I add H2 is a hydrogen's going to come along here, and the hydrogen I'm going to break 2 bonds. So I'm going to break the bond between the hydrogens, and I'm going to break one of the CC bonds, and I'm going to draw, so I broke 2 bonds, and I'm going to form 2 new bonds, so now I have an alkene. And I'm going to take another H2, and I'm going to do the same thing. I'm going to get rid of the HH bond and one of the CC bonds, and I'm going to, now that those 2 are gone, I'm going to create 2 new bonds between carbon and hydrogen, and now I have an alkane. So when I add excess hydrogen to an alkyne, it will turn to an alkene and then to an alkane. Right? If I only add enough hydrogen just to get rid of the alkyne, it will become an alkene, a double bond. Okay, my second question there is B. B says, what happens if I have an alcohol with hydrogen chloride? Let me get rid of this. Alcohol with hydrogen chloride. Okay, the second question here is when we add an alcohol with hydrogen chloride. So an alcohol could be any hydrocarbon. come on, with an OH at the end. Here's my alcohol, and I'm going to add to it hydrogen chloride or hydrochloric acid. Now what's going to happen is the chlorine here is going to see the OH group, and it's going to kick the OH group off. So I'm going to get HOH on the right here, which would be water, plus my other malt compound, which would be a haloalkane. So where I originally had an OH at the end of my hydrocarbon molecule, I now have a chlorine at the end of my hydrocarbon molecule. And where I had H coupled to Cl, now I have H coupled to OH. Okay, so it is a substitution reaction. Sorry, I think I said addition. It's a substitution reaction where the chlorine goes on and the OH comes off. Okay, so there's substitution. Now, so the first one was addition, alkyne adding H2. The second one is a substitution. The third one is my elimination reaction. So again, let's look at the elimination reaction here. Elimination reaction, I know it's elimination right away because I see this sodium ethoxide, that special compound that rips hydrogens off an alkane to turn it into an alkene. So I've got a haloalkane in this case, so let's make it, undo. CH3, CH2, and chlorine. There's my haloalkane, it's chloroethane, and I'm going to rip off the chlorine and I'm going to rip off one of the hydrogens. So this carbon here is going to lose the chlorine, and this carbon here will lose a hydrogen. By both of them losing an atom means they both need to form a new bond, and what I'm going to do is I'm going to put a new bond in here once this becomes a 2 and this disappears. So I'll end up with CH2 double bond CH2, right, where I originally had CH3 and a single bond, and CH2 and chlorine. Let's put my chlorine back in there. Okay, so I'm going from there down to here, and I'm releasing really the hydrogen and the chlorine. It's more sophisticated than that, but for all intents and purposes, that's all we need to be thinking about. And then our last question here has a carboxylic acid reacting with an alcohol. Again, so that's my formula for an esterification reaction to make an ester. Okay, so let's erase this one. Whoops. And let's look at my carboxylic acid. Something C double bond O bond OH reacting with an alcohol. The alcohol, in this case, I'm going to, again, it's handy to write your alcohol backwards instead of OH. It's always HO because it's the O that's bonded to the carbon, right? It wouldn't be OH-C. It's HO-C because the H is the one that's coupled to oxygen and the oxygen's coupled to hydrogen. Now again, remember what's going to happen here is I'm going to remove the OH from the carboxylic acid and the H from the alcohol, and now the O can bond up to the carbon here, and what I'll end up with is C double bond O bond CH3, right, where this OCH3 here is now here, and this hydrocarbon C double bond O is still here, hydrocarbon C double bond O, but the O now couples to C. Okay, so this is an ester that we've made. There's my ester, and that's esterification is the type of reaction, okay, making an ester. If I roll up to question 10 here, it says identify each reaction as a combustion, addition, elimination, substitution, or esterification. So the first one I'm seeing the OH is going to be replaced by a Br. Right, so this Br here, in the HBr, is going to, this Br is going up here, and the OH is coming down here. So that is a substitution reaction. Right, again, remember, it's just like a double replacement reaction, double displacement reaction, where I end up with HOH over here, which is water, and I end up with my bromopropane, and here I end up with my propane with an alcohol, or propanol. If I look at my second reaction down here, I'm seeing a hydrocarbon reacting with oxygen, to make carbon dioxide and water. That's combustion. Right? And it's actually complete combustion, because it's possible this could be incomplete, and I would also make carbon monoxide and solid carbon, right, if it was incomplete. And you think, well, how is that possible? I only have one carbon on the left, and now I have 3 carbons on the right. I'd have to balance that equation. So it's not balanced. All right, but there's a possibility. So the way it was originally, that is complete combustion reaction. If I roll down to equation C, I'm seeing my sodium ethoxide there. So there's that sodium ethoxide molecule, which is going to take the iodine off one carbon and a hydrogen off the other, right? And what I'm ultimately going to do is create a double bond in between those 2 carbons, right? So I'm going to end up with this structure over here, right? And that is an elimination reaction, where I'm removing parts from a haloalkane. I'm turning it into an alkene. All right, so reaction 1 was substitution, reaction B was combustion, reaction C is elimination, reaction D, I'm seeing, right off the bat, I'm seeing 2 reactants. One is a carboxylic acid and one is an alcohol, so I know it's going to have to be an esterification reaction. So again, remember what's going to happen. The OH is coming off here, the hydrogen's coming off here, and then this O will now couple to C. Right, so I've got CH3C double bond O, CH3C double bond O from that left molecule, and I've got CH3CH2O on the right molecule, CH3CH2O, and notice I've had to turn this molecule around, which is why I usually draw it the other way, because the O from the alcohol has to couple to that C, all right, to make the ester. And then there's my ester linkage right there. There's my ester linkage right there. And then the last reaction, I'm adding an H and a Cl across a double bond. So I'm going to take my H Cl molecule, and these 2 bonds are going to form, and this bond is going to disappear, and this bond is going to disappear, and I end up with a haloalkane. So I'm starting with an alkene on this side, double bond. It's actually propene, 1, 2, 3 carbons with a double bond, propene, and I'm ending with chloropropane on the right-hand side. We're at a haloalkane. And in question 11, the last from the homework, says draw the structural formula for the organic product that's predicted, propene plus HBr. Draw the formula. Okay, so I'm going to start with propene, CH3, CH, double bond, CH2. So there's my propene. Again, remember, always be counting your number of bonds to carbon. Right? This carbon has 3 hydrogens, so it needs a bond. This carbon has 1 hydrogen, it has 3 bonds. This carbon has 2 bonds, so it needs 2 hydrogens. So I'm always counting my hydrogens. Now I'm going to add an HBr. Okay, HBr is going to come and slot itself in down here. Right, and then I'm going to break 2 bonds and form 2 bonds. So I'm going to break this bond, and I'm going to form this bond and this bond. So I end up with a CH3, CH2, CH2Br which is a haloalkane. It's bromopropane. Okay. This molecule here, this formula here, or equation here, I'm seeing the H2SO4 in there, which often tells me that it's going to be an elimination reaction. Remember, there's two ways for an elimination reaction to happen, using H2SO4 or sodium ethoxide. So in this case, I'm going to remove the OH from one side, and I'm going to remove the hydrogen from the other side, and I'm going to form a double bond in there. So I'm going to end up with CH3, CH2, CH, double bond, CH2. So notice that the carbon over here, CH2, has still got its two hydrogens. It lost the OH. The OH left with the hydrogen. So remember, I also get another product, HOH. Right? So this is an elimination reaction. So I had an addition reaction up here. I have a elimination reaction here. This one here, I'm seeing, well, there it is again. I'm seeing my carboxylic acid and my alcohol. Right? So I'm going to again remove the OH from the carboxylic acid. Remove this with the hydrogen from here to form water. And I'm also going to have my ester formed using the CH3, C double bond O on the left. Doesn't really matter how you draw it, but this is kind of the usual way to write it. CH3, C double bond O. And then I'm going to couple it to the O from the propanol, and then add my CH2, CH2, CH3. Right, so that becomes my new molecule. That is an esterification reaction because I am forming an ester there with the alcohol and the carboxylic acid. Okay, so you'll see there's not a lot of options here. I can make this happen a lot of different ways, but there's really not a lot of options. So there's all of our homework from the other night. Okay, so as we move into 4.6, 4.6 looks at organic compounds, and it just kind of reminds us that organic compounds are all through our society. They're in our medical system, in terms of pharmaceuticals, in terms of materials that we use, in terms of syringes, plastics, catheters that we use, disposable gloves that we use, over and over and over. When I think of medicine, I typically think of pharmaceuticals, but there's so many other things too. Right? The plastic ends on the thing that they test your temperature with when they put it in your ear. Right? It just goes on and on. The little plastic vials that they pee into. Okay, all organic chemistry. It's in industry. We're going to see some examples of that today. It's through farming in terms of the chemicals that we put on our fields, pharmaceuticals, and equipment that requires specialty materials, construction materials, transportation materials. And again, we're going to see lots of examples of these. And ultimately, the whole goal here is to improve lives. Right? We're not just making them for the sake of making them. We're making them because ultimately they are supposed to be there for the common good or for the good of specific people. The problem, as we're going to see in 4.8, is that they can also be harmful. Right? They can be bad for us, or they can be bad for the planet. If they're bad for the planet, ultimately it's bad for us either in the long run, because it will come back to haunt us. So the table here just gives us a quick look at some common organic compounds. Three of them are medications. ASA here is aspirin. Okay, it was originally released into the world as aspirin back in the probably it's the earliest and probably the most prescribed medication ever in the history of the planet is aspirin, believe it or not. There are still, when I'm watching stuff on the computer, I often see ads for people who think they're having a heart attack or a stroke, and they say, chew 2 children's aspirin and call 911. Right? That's what you do if you think you're having a heart attack or a stroke. Chew 2 children's aspirin and call 911. Right? A huge molecule for the world. It does lots of good. And there are also some possible side effects from from aspirin. So ultimately, we use it for getting rid of fever, for inflammation and pain. It can cause stomach upset, and it can actually be associated with a bleeding disorder. With a syndrome called Ray's syndrome, which basically can affect the liver and brain of children and teenagers. So I've never seen anybody with that syndrome, but I read about it in a lot of books, and I'm sure it's probably not that uncommon. Acetaminophen, when it was first released, was Tylenol. And Tylenol, today it's released as a number of other drugs. Advil also. There's a number of different drugs that contain, I think Advil's ibuprofen, sorry. Acetaminophen, Tylenol is in a lot of different medications, though. Right, lots and lots and lots of people taking Tylenol, again, for fever and for pain. Oh dear. Fever and pain, right? But again, they can upset your stomach, and large doses of Tylenol can affect your liver. Lidocaine, which is another pharmaceutical here. Again, some of you may have used this at some point in your life if you've had a bad sunburn. Right, you may have taken lidocaine. Lidocaine usually spray on, and it cools that sunburn. It's also a little bit of an anesthetic. So if you're having a tube put down your throat to do gastroscopy, to look at the inside of your stomach, looking for ulcers or any other things, they will spray the back of your throat first using this local anesthetic for the back of your throat, and that would be lidocaine also. And again, there are people who can have swelling in response to this particular medication. So there's always a risk, right? There's a benefit and a risk, and we're going to talk about risk-benefit analysis a little bit later in this chapter. There's an insecticide here called carbaryl. Again, people spray it on their lawns so that the insects don't come and leave huge patches on your lawn of dead grass and eat your grass. And the reason why we liked carbaryl was because it's not toxic to us. It's not toxic to people who have dogs and cats and pets that go outside to play with on the lawn with them. However, we know that once it gets into the aquatic ecosystem, it can be very toxic to fish, and also not just the insects that we're trying to kill, but also non-target insects such as honeybees. And again, we know that as the honeybee population in the world is going down, so are all of our pollinators, and we're going to end up in big trouble before long because we can't pollinate our apples and peaches and pears and cherries and vegetables and all kinds of things that need pollinators. We've got an artificial sweetener called aspartame. Aspartame, again, was developed for people who were trying to lose weight, but still had a weakness for sweet things, so you could eat sweet things without gaining any weight. But the problem is, when they were first discovered, we originally thought they were safe, and it was proven that they were safe, so they approved it, FDA in the US, and then in Canada approved it. But today, there are people who believe that it might be associated with a certain amount of risk to your health. But again, it's still all over the place in all kinds of foods. So I still think it's probably deemed safe at this point in time. I know I ate foods that contain aspartame every once in a while. Menthol is another chemical. It's an organic compound. We use it to make toothpastes minty. It goes into mint-flavored chewing gums and certain types of cough syrups that are there to try and suppress the cough reflex. But again, the negative side of this, again, there are a small number of people who will have allergies to this molecule. There's another chemical called MSG. MSG, monosodium glutamate, is a flavor enhancer. It's put into recipes, makes people think that something tastes super good. But what it can, and for a lot of people, it does enhance the flavor, so people do exhibit a greater taste sensation, a flavor sensation. However, there are a number of people who have allergies to MSG, and it can cause a number of different effects in those people, including migraines, and people who have asthma can suffer from MSG. It can cause an asthmatic reaction or attack to be a lot worse. We've got a chemical called TCE, trichloroethane. that's used in the dry cleaning industry. If you take your clothes in to be dry cleaned, that's one of the chemicals that are used. However, there are a lot better chemicals today. I think most dry cleaners have moved away from it because it's very bad for you. It's bad for your nervous system, which means your brain and your spinal cord and your nerves. It's also bad for your kidneys and your liver. We've got a chemical that goes into our cars to cool our engines. It's called ethylene glycol. It's that green stuff that you put into your radiator for an antifreeze. That means in the wintertime, your engine won't freeze up. Again, if your antifreeze system in your car froze on a -40 day, you wouldn't be able to turn your car over, and freezing might crack or do damage to your block, or your parts of your engine. So we put ethylene glycol. It's in everything. It's in buses, cars, motorbikes. It's all over the place. The problem is if you're in an accident, it's a front-end collision, the radiator is right there behind your bumper, and it's the first thing that gets hit, and you'll always see that big green puddle on the ground after the accident. And the problem is it's very toxic to pets. It smells good. It tastes sweet. So a lot of animals will smell it and they'll start drinking it, and they'll drink as much as they can, and ultimately it's very bad again for their nervous system, for their brain and nerves and spinal cord, and also can cause heart failure. And then the last one that's on our list here is acetone, and again acetone for nail polish remover. Again, very good for what it does, very effective nail polish remover. However, again, you probably already know there's some controversies about using acetone-based nail polish removers. Today there's a lot of acetone-free. Some people would argue they just don't work that well. But again, you don't want to be working around something where the fumes are all around you and they're highly flammable. It could be very irritating to some people. Their eyes can get really irritated. They get red and scratchy and with water. Again, watery nose, scratchy throat. Right, so all these kind of effects from acetone. So all these different chemicals in all sectors of our lives, even in our homes, are being used for different things. Now, the last topic in Chapter 4 has to do with a group of chemicals called polymers. Polymers are a group of molecules that are long chains of small things that are glued together. Just like we have letters that make up words, and letters that make up sentences, and letters that ultimately make books, we have these things that are glued together, and they're very small for the most part compared to the size of the molecule of the polymer. And the small bits, so again, you can see in the example down here that I have all these little red dots that are joined together to make a long chain. These little red dots are forming the chain. The chain's called a polymer, and the little red dots are called the monomers. Mono means one, poly means many. So we're undergoing something called a polymerization reaction, right? We're making a polymer by joining together many small building blocks together called the monomers. Now, at the end of the day, these things can be thousands or even tens of thousands long, so they just continue to grow, right? And I can store a lot of molecular information and or energy, whatever it is I'm storing, in this one long chain molecule, in this one polymer molecule. So it becomes very efficient. Down here you can see that I'm alternating red, blue, red, blue, red, blue, red, blue, and it will continue red, blue, red, blue, red, blue, red, blue, all the way along, and it would go on forever and ever for thousands or tens of thousands or even hundreds of thousands long. And the question is, what are the red and the blue? What is the circle and what is the square? Okay, well, before I go on to what they are, what the monomers are, different monomers will create different polymers, right? So, again, if I could put a bunch of A's together, I would probably get a sound that says A. If I put a bunch of E's together, I'm going to get a different sound altogether, which is E, right? And by putting different monomers together, I get very different effects. The same thing here. So the whole goal of a polymerization is to have something repeating, right? It's got to repeat. Now, down here I can see I've got something which has got 3 parts to it, coupled to something blue that's got 3 parts, coupled to something red that's got 3 parts, coupled to something blue, and again you can see what the pattern would look like as it continues to grow. So that's a polymer too. So all of these polymers are made using polymerization reactions. The reaction is what glues the monomers together. It's what joins them together. Now if I scroll up here, there are 2 different kinds of polymerization reactions. The first one's called an addition polymerization reaction. In addition polymerization, it's just like addition that we had before. I need a double bond and I'm going to add something across the double bond. Here what I've got is my molecule tetrafluoroethene. Tetrafluoroethene. Tetrafluoro, 4 fluorines. Ethene, 2 carbons with a double bond. So there's my tetrafluoroethene, and there's another tetrafluoroethene. This is the monomer. Okay, and then what's going to happen is I need to join them together. So the way I'm going to do that, just like we did in the addition reactions earlier in this chapter, is I'm going to break I'm going to break one of these bonds and just leave a single bond. I'm going to break one of these bonds and just leave the single bond. And then what's going to happen is, where does the missing bond go? Well, it goes to forming a bond between this carbon and this carbon, between this carbon and the next one. So I end up with CF2, 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 and this huge long chain of CF2s called polytetrafluoroethene, PTFE. And when that was discovered back in the 60s or early 70s, I think, it made a non-stick coating that we put on frying pans because it was strong and very heat resistant and very stable, and it was called, by the company that made it, a chemical called Teflon. Okay, Teflon was again you can kind of see where the name kind of came from, tetrafluoroethene. And this thing was made as a coating on the inside of this frying pan that we can see here. And in doing so, I've got a nice non-stick surface. So like I said, the beauty of this thing is that it's very stable. It doesn't decompose very readily. It won't come off in my food. It won't get washed off. And it's lovely to cook with because food won't stick to it. Food won't burn as readily. And it cleans up very, very easily. So I'd say probably half of the kitchens on Earth have got a non-stick frying pan, if not more. And they are just a staple. Again, in the 50 or so years since it was discovered, it's become a very important part of most kitchens. So there's an addition polymer. Okay, I'm going to talk about 2 more popular ones in a minute. Okay, we also have our second type of polymerization reaction. Let me erase some of this, which is called a condensation polymerization reaction. And in a condensation polymerization reaction, I see the word condensation. I think, what's condensation? Well, that's when I wake up in the morning and find water, the lawn is wet. Find the windows on the car are wet, or the windows for the house. You've been cooking and they've all steamed up. Okay, condensation happens when water forms a layer, and that's exactly what's happening here. This is an esterification reaction that we're going to be talking about, and I'm going to need, instead of having one monomer that I'm going to repeat over and over again like I did in that addition polymer, I'm going to have 2 different monomers here. One is an acid, and it's actually a diacid. It's got a carboxylic acid at one end and a carboxylic acid at the other end. The other molecule is a diol. It's got an alcohol at one end and an alcohol at the other end. So what's going to happen here is condensation. I'm going to remove water, remove the H2O. So there's my OH, there's my H, just like we were doing before. They're going to give me HOH, and I'm going to end up forming an ester. So there's my ester linkage there. and then this OH over here is going to bond to the left carboxylic acid on the next terephthalic acid, and then the right one of that terephthalic will bond to the next ethane 1,2-diol. So that example of a polymer that we had up here that was blue, red, blue, red, blue, red could be just like the one we're just doing here with the ethane diol with the dicarboxylic acid. Ethane diol, the diacid, the diol, the diacid. So just to finish up here, we're looking at our two types of polymerization reactions, two types of processes that I can couple together monomers. Right? One is the addition polymerization, where I'm going to take my molecules that have double bonds, and as we do in any addition reaction in organic, I'm going to add something to both carbons in order to get rid of the double bonds. Right? And then I just continue making my long chain here that will grow and grow and grow and grow. And then in condensation polymerization, I have the esterification reaction where I need to have carboxylic acids and alcohols. Some molecules actually can do this by having a carboxylic acid at one end and an alcohol on the other. So what happens is the carboxylic acid at the end of one will bond to the OH group at the end on the end of the other one, and then by an ester link. And then the carboxylic acid at the end of that one will bond to an OH on the next one. So I have whatever the structure is, my hydrocarbon piece in the middle, but then I'm going to have a COH on one end. That was messy. And I'm going to have an OH on the other end, so that I can always have the OH on one end bonding to the COOH on the carboxylic acid on the next molecule. And then it just continues again. And then I'll have that circle, 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 circle type of addition polymerization again, where all of the monomers are the same. Okay, so lots of different possible configurations, which is why there are so many different polymers. Now, today I want to talk just quickly about a few polymers. The first one is called polystyrene. For polystyrene, this is an addition reaction, and what I've basically got here is CH2 try this again. I have CH2 and then double bond and then CH and then that hexagonal shape thing, which turns out to be a 6-carbon ring structure. And then what's going to happen is this monomer with the double bond will undergo addition reactions, and then I'll end up with a polymer that looks like this. There's one polymer, there's the next monomer, there's the next monomer, there's the next monomer, until I end up with my great big long polymer chain. This molecule here is styrofoam. It's called polystyrene. It's styrofoam. It's the same styrofoam we find in so many different things. If you go and take out food and it comes in a styrofoam container, that is polystyrene. If you get insulation, right, something, you buy a new TV and it comes with styrofoam packaging, right, that's all polystyrene. Styrofoam cups, styrofoam anything. Right? It's just amazing how much styrofoam we have in our lives, kind of all over the place. And it's this very simple molecule that's made by an addition reaction. Okay, our second type of molecule, again, hugely important in the world, is called PVC, or polyvinyl chloride. Now, if you take a tech course at the school or other, you will learn about PVC. It will grow and grow and grow and grow. And then in condensation polymerization, I have the esterification reaction where I need to have carboxylic acids and alcohols. Some molecules actually can do this by having a carboxylic acid at one end and an alcohol on the other. So what happens is the carboxylic acid at the end of one will bond to the OH group at the end, on the end of the other one, and then by an ester link. And then the carboxylic acid at the end of that one will bond to an OH on the next one. So I have whatever the structure is, my hydrocarbon piece in the middle, but then I'm going to have a COH on one end. That was messy. And I'm going to have an OH on the other end, so that I can always have the OH on one end bonding to the COOH on the carboxylic acid on the next molecule. And then it just continues again. And then I'll have that circle, 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 circle type of addition polymerization again, where all of the monomers are the same. Okay, so lots of different possible configurations, which is why there are so many different polymers. Now, today I want to talk just quickly about a few polymers. The first one is called polystyrene. For polystyrene, this is an addition reaction, and what I've basically got here is CH2 try this again. I have CH2 and then double bond and then CH and then that hexagonal shape thing, which turns out to be a 6-carbon ring structure. And then what's going to happen is this monomer with the double bond will undergo addition reactions, and then I'll end up with a polymer that looks like this. There's one polymer, there's the next monomer, there's the next monomer, there's the next monomer, until I end up with my great big long polymer chain. This molecule here is styrofoam. It's called polystyrene. It's styrofoam. It's the same styrofoam we find in so many different things. If you go and take out food and it comes in a styrofoam container, that is polystyrene. If you get insulation, right, something, you buy a new TV and it comes with styrofoam packaging, right, that's all polystyrene. Styrofoam cups, styrofoam anything. Right? It's just amazing how much styrofoam we have in our lives, kind of all over the place. And it's this very simple molecule that's made by an addition reaction. Okay, our second type of molecule, again, hugely important in the world, is called PVC, or polyvinyl chloride. Now, if you take a tech course at the school or other, you will learn about PVC very, very quickly. If I go to, I had some examples of PVC on, maybe I don't have them examples. No, I don't have the examples up anymore. PVC is a bunch of tubing of pipes that can be used for a number of different applications. Look for PVC pipe and look for images. We'll see lots of examples of PVC pipe, right? And it's used for all kinds of things. Again, lots of applications through industry, through building and construction, all over the place, right? So that's all PVC, and you can see, yeah, that's actually probably going to have a pretty big application, and it does. It is again, multi-billion dollar industry. So that's PVC. And the other one that we're going to talk about in a minute is ABS pipe. ABS pipe, again, is used for all kinds of different things. It's used in plumbing. Right, you can see it there, that picture in the middle, The nice thing about this stuff is you take your pieces and you just slot one piece, into another. So you put a bit of glue in there first. The glue comes in a can like this, and 1 minute later, and it is sealed tight and will never leak, ever. 100 years from now, 200 years from now, it will still be solid and will still not be leaking. Right? So the advantages of using PVC pipe, again, are just enormous. Right? Much better than what you can see in the picture down here with all the metal pipe and it's going all different directions. The PVC pipe really is very, very kind of flexible in the way we use it, and a very powerful tool. And you can see the one that's in the middle here. A bit of a plumbing nightmare. You've got a big wrench there trying to take the bottom piece off. It looks like there's pipes going every which way. It looks like there's a rag wrapped around one that's probably leaking. All over the place, just a big mess. So PVC has really changed the world of plumbing. I'll come back to PVC in a minute. So nylon 6. Nylon was made back in the 1940s and then became quite popular around that time for nylon stockings. Right? And before that time, if you wanted to wear something on your legs and you were wearing a skirt or a dress, you would have had to wear something that was made of cotton or wool. Obviously not quite the same thing as nylon. So nylon was back then almost considered nude, and it was a huge revolution in the way it worked. And again, it's an esterification reaction. Nylon is used in ropes. Nylon is used in clothing. Ropes and clothing. When I say clothing, you think, why is there nylon in clothing? Because what you can do is if you're making a shirt and you cut the piece out for the sleeve, and then you want to sew the sleeve onto the rest of the body of the shirt, you use a bit of nylon to attach the sleeve to the shirt. Right? If you have a hem at the bottom of your pant leg or the bottom of your sleeve, and you want to sew up your pant leg to put a cuff on it, then you'll basically probably use nylon. Right? So again, lots and lots of places. A lot of the fabric that you might be wearing at this moment probably contain nylon. And it's called nylon 6 because it contains a 6-carbon monomer. There are 5 CH2s and then another carbon. So it's got a 6-carbon monomer. And this is a slightly different it's not. It's a condensation reaction, not exactly an esterification reaction. And then the one down here, the last one is Dacron. Dacron is another fabric that was produced, and again has lots and lots of application. It's in a lot of athletic wear. Very stretchy, very durable. It washes well. It cleans well. It's perfect for the hospital, where people will be wearing them, and then they'll get blood on them, or they could get in really bad shape really fast. So they need to be washed. So they make for good clothes, good heavy-duty clothes, work clothes. Right, so you're seeing, again, lots of uses for these polymers. Polymers are organic compounds that basically are long chains of monomers. So I'm not going to get into thermoplastics, but we kind of get to the bottom here where we're looking at our codes for different types of polymers, and I'm seeing the first one is the PET, which is the polyethylene terephthalate that we talked about before, PET. The second one is polyethylene or polyethene. The next one is polyvinyl chloride, which is all of our styrofoams. Our polystyrene down here is styrofoams. Polyvinyl chloride is all of the pipes that we used inside the house for plumbing. And we've got low density polyethylene for plastic bags and plastic food wrap. Polypropylene, which are slightly harder but still soft. They will not break if they're dropped. Things like yogurt containers and margarine containers. There's your polystyrene down there. And then lastly, plastics such as those used for, say, outdoor patio furniture, like the hard plastic, the white hard plastic stuff, would be in this category number 7. All right, so there's the world of organic chemistry and uses for organic chemistry. So we started chapter 3 just looking at hydrocarbons in general, and then from there we went into looking at naming alkanes, alkenes, and alkynes, and adding branches to it. And then we talked about the different families by putting different things on our alkanes. And then in this chapter we've looked at chemical reactions to change the things that are on hydrocarbon chains, add them, to remove them, to couple them together. Lots and lots of possibilities. And then we've seen where they're used, and they're used everywhere. So part of our responsibility as a chemist is to try to decide whether or not we should be making some of the stuff that we make. Right? At the end of the day, when we make something, the reason why it's being created is because it's got some benefit for either a small part of the population or a big part of the population, but there's a benefit to be had there. The problem is, with most things in life, there's going to be some amount of risk that comes with that. And what we always have to do is balance and say, is there more risk than benefit, or is there more benefit from risk? Because if the amount of risk is so high that it completely overrides the benefit, then it's not worth doing. That's where, again, if I get on my hobby horse here about vaccinations, the people who are the anti-vaxxers will say, oh yeah, vaccines are not safe. And they're right. There is a small chance that somebody somewhere will have a bad reaction. However, the risk of something bad coming to somebody who gets a vaccine compared to the 100,000 people who have a benefit from it that don't have any bad effects, you say, well, maybe there's more benefit here than risk. It's worth the small amount of risk to have that a maximum amount of benefit. All right, so again, as we're thinking about organic compounds, we need to be thinking about the risks associated with it, because they're not the safest molecules under the sun. Okay, so just to finish up then. So we've talked today about addition polymers, we've talked about condensation polymers. These are all in the note that I just talked about. The issues, right, some of the organic compounds and the chemistry make some of the nastiest chemicals that are known to humans, right, are made by as organic compounds. Those that are mutagens that cause damage to genetic material. They're carcinogens, they cause cancer. They're teratogens, they affect unborn children. Some of these things are kind of buried in the world of organic chemistry, and we again always need to be aware of the fact that we're playing a little bit with fire here when we're playing with organic compounds. Potential for a lot of good, potential for some really bad stuff too. Okay, so again, that being said, I shouldn't try and say that organic is a bad thing. I think organic has changed the world infinitely for the better. We just may have to make sure that we have to steer clear of making poor choices as chemists and as citizens of this world. Okay, so I'm going to leave you with questions here on page 150 in our textbook. Those are specifically about polymers and about those chemicals we just talked about. Again, we talked about this chart earlier. I don't expect you to remember any of these drugs or the pesticides or the food additives, or right, you don't need to remember all that. I think it's really just important to recognize that as good as a lot of these things are, they also come, as we have seen, as we've seen earlier, with a lot of possible harmful effects too. Okay, so now that we're done Chapter 3 and Chapter 4, I've already assigned the review for Chapter 3. I'm going to leave you with the review for Chapter 4 also. This is a big review, so I'm actually going to assign a lot of it because I really want you to be able to spend some time between now and our test looking at this. Our test is booked for, I'm going to pull it up on my other computer, which is here beside me, because every time I've tried twice today to switch to my calendar, and it has kicked me out of the video and I've lost my video. So I am looking at, if you look at the hub, I will try this in a minute. Actually, I'm not even going to try it. If you look in the hub, you will see that the SCH4C for Unit 5 is due today. This note, 4.6 and 4.7, is for tomorrow. We're going to have a live class to look at any of the review that you'd like to do on the 27th on Wednesday, and then our test on both of those organic chapters. Chapter 3 and Chapter 4 will be together as a single test on Thursday, and I'll give you more details about that test. I'm going to work on it tonight and tomorrow. So by tomorrow night I should be able to give you some test details. By Friday I'm going to be ready to start Chapter 7. I'm going back to a little bit of environmental chem, and on Monday your last career assignment is due, and then you've done all the STSEs and